Hello, this is a podcast which we haven't named yet. We have no idea what we're doing, but like any good pilot episode, we're going to try and go through and record it in one take. Today we're going to be discussing the concept of energy. I've got two other people with me, one of whom just made like a chef's kiss sign gesture with his hand. I think that was commenting on this introduction being amazing. So, yeah, I'm getting a thumbs up. So anyway, I'm Calvin. Next to me, I've got
Rob.
And we've got,
Ollie.
That's so funny. It's your own name.
This is probably what every single thing is going to devolve into. So, for a bit of context, we're all physicists. We're all studying physics at university. And, yeah, I guess this is a substitute for a social life. Anyway, so I got a list of questions from some friends on the internet about physics, and most of them were like incredibly existential. But the question I think that would be most interesting to a video on is energy. What is energy? Why do we care about it? What the heck is going on? Why do physicists keep writing stuff about it? So, anyone want to start with their thoughts?
So first way that I typically think about it, in a very basic way, is kind of from where the idea for energy first comes from. And the way that I typically show where energy comes from is from Newton's second law, right? You can kind of integrate up Newton's second law, and your energy term comes out as a constant of integration. You get kind of an expression for kinetic energy, an expression for your work done, kind of an integral of f dx, and you also get a constant of integration.
And as we all know, work is the most trivial result in all physics.
This is true.
So this is there was a whole question as to whether or not I would attempt this impression of one of our lecturers at the start, and I promised I wouldn't. But now the recording started, they can't stop me.
Restart.
What's the time step? What's the meaning?
So do you want to actually explain a little bit more about what you mean by like integrating up?
Yeah, so
Newton's second law.
Newton's second law in the constant mass form is F equals ma, as you know. And the acceleration can be written as, well, acceleration is rate of change of velocity, so dv by dt in the motion calculus. And we can use the chain rule to express dv by dt as dv by dx times dx by dt, which is the velocity. So we now have Newton's second law in the form of F equals the mass times the velocity times dv by dx. If you now integrate both sides on the left hand side, you get the integral of f dx, which is kind of your work done, or we can interpret it as your potential, depending on how you're feeling. And on the right hand side, you have the integral of mv dv, and you get half mv squared. And kind of then you have a constant integration, which you can interpret as your total energy. And this doesn't change because it's a constant.
Okay, so if anyone actually managed to follow derivation, there's an amazing thing there where Ollie was writing down the derivation on his pad as he went. This is the issue. We don't know what we're doing here, and like it's kind of hard. I realised I said that. How am I going to make Ollie explain integration in a simple way
without waving hands?
We're not used to doing this. But yeah, so I think the simplest way to think about that is, energy, or at least one way of looking at energy, comes out from just Newton's equation of motion. It is just something which appears to be constant, then, more or less, and it's just a way we can... It's, I guess, so one quite neat thing about energy is, like, if you just had a force, and you were trying to work out like the velocity something has, you could go through the route of, okay, well, force is, as Ollie said, ma, which is the mass times rate of change of acceleration. If I know the force, I can work out the acceleration, and from the acceleration, well, if I know the rate of change of velocity and I know the initial velocity, I know the change in the velocity, so I can work out what the velocity goes to. But sometimes this can be really, really, really difficult. Like, it's quite simple if the acceleration is constant, but if the acceleration varies as I move, suddenly we get really complicated differential equations that you can't really solve very easily. And energy is a lovely simplifying factor. It takes out all of the stuff that happens in the middle and ends with just the stuff that happens, well, at the start and at the very end.
Yeah, so yeah, I think that's like exactly spot on. And I think it's worth emphasising that in kind of the Newton's formulation mechanics, you can either just work with Newton's laws, and as you say, that kind of gives you everything, or you can just use conservation of energy and conservation of momentum. They say nothing more than Newton's laws do on their own. You can derive one from the other and vice versa.
Yeah, it's worth noting that all of Ollie's derivation would work in reverse.
Yeah, what's neat about that really is with Newton's laws, you take a very local sort of picture. You've got to sort of consider each nudge as you're pushing the object along and imagining how it's going to evolve at each point in time. The beauty of considering something like energy, which is a conserved quantity, something so valuable to us, is that, like Calvin said, you only have to look at the beginning and the end, or you can pick any point in between. You don't necessarily need to care the exact details of the passage in between. You know this quantity is going to stay the same on either end.
Which I think actually introduces a really, really important and interesting point about energy, which I think we'll probably come back to, which is the notion that it's path independent, or at least it is most of the time. maybe this will be a thing we'll come back to. Maybe this is foreshadowing Calvin's doing. I don't know. But yeah,
Smeagol.
yeah, I may only refer to myself in third person. I just failed at that anyway. Yeah, so yeah, I think that's a really important point to look at because like quantities only exist in physics because they're useful for making predictions. And energy has one really, really powerful property, which is that in a certain set of situations, not all situations, it doesn't depend on the path you take between 2 points. It's just a function of where you start and where you end.
I think it would also be nice to kind of point out that there's kind of something more to just the fact that energy is conserved, but it's also conserved locally. So energy, and the same as kind of thinking about kind of charge and electric current. So you don't have charges disappearing in one place and appearing in another. You have them flowing from one place to the other. So you have a current from one place to the other. Similarly with energy, you don't have energy kind of disappearing in one place and appearing in another. If your energy kind of associated with particle, if your particle's moving from place to place, that energy is kind of being continuously moved over there. And so I think there's something deeper about kind of the local fact that it's a local constellation, or rather than just global. And obviously, global constellation follows from local constellation. But yeah, I just think that's kind of something interesting to think about.
And of course, physics kind of relies on the notion of locality to begin with. It's something that I feel we don't get talked about very early on. We don't mention, but physics has some underlying assumptions, and those underlying assumptions are that the methodology we have used to come up with physics works. And one thing that really, really would cause a problem with this is if, in order to discuss the way I'm going to throw my pen on the ground and it's going to make a noise, in order to discuss exactly how that pen moved, you don't need to look in order to work out more or less what's going on, in order to work out the parabolic trajectory, or maybe not a parabola because I didn't throw it exactly from the centre, but something quite close. You don't need to know about the motion of a galaxy a long way away. If we did, we'd never have arrived at physics, etc. These guys would probably be laughing because they realise that whilst I think I'm being very clever, I'm basically quoting what our lecturer said a couple of days ago.
It was a very good lecture.
He was an incredibly good lecturer. Yeah. So I think that's, it's a really nice thing. There are certain things we expect physics to do, and energy and this locality is one of those. I guess moving on, I don't know if you guys want to talk about dissipation of energy, stuff like that, or...
Yeah, sure, yeah.
Yeah, okay. So what do you want to go?
So off with us then, yeah?
Yeah.
So first thought is dissipation is kind of a result of what you're considering for your system, I think. So if you only have kind of a particle sliding on a surface, which is friction full, so
Frictionate.
If you're just considering the energy of your particle,
Sorry, I really appreciate frictionate. Finite but frictionate. Finite friction. Sorry, Ollie.
okay.
Thank you, Rob.
Yeah, so if you're kind of only considering your particle on its own as a system, then the system is losing energy, and that's because it's being dissipated into kind of other forms. If you kind of take into account all of these forms of energy, energy is still conserved.
I think that is a very interesting point you bring up about different forms of energy, and in some ways it can sometimes feel quite artificial, this counting game we play as physicists, where maybe you start with a simple notion of, like Ollie introduced, kinetic energy. We look at work, introducing a force and pushing, but then there are many more other forms of energy that may feel more contrived and elaborate. Something like potential energy still feels quite natural, like we can imagine that with a change in height, we've still got our force act, and we've got this notion of work coming through still. But then we end up with energy due to charges moving in an electric field, which is still force, but now getting more contrived again. And then even more abstract forms of
Nuclear
energy.
energy.
Exactly, eternal energy, these very large, overarching
And
terms.
I guess the really famous, scary example is mass energy. This
Yeah,
famous
yeah,
equation
yeah.
equals mc squared, which basically says that, haha, you think you understand energy. No, you don't, pranked. Energy and mass, same thing, and somehow simply having mass, even if something isn't moving, isn't in a potential, still has energy. I guess one very common way of phrasing it is that mass and matter is simply a super concentrated form of energy. Don't know how rigorous that is, but but yeah. So one other thing, which I guess we're going to have to get onto at some point, discussing things we want our laws of physics to have. We mentioned locality.
Mm-hmm.
One other thing we would really, really, really love physics to have is time invariance. I mean, these guys were wondering when I would come onto this. So because
It's bound to happen.
yeah, exactly. Because when you think like physics, what does physics really aim to do? Well, physics aims to predict the future. Like ideally, we want to do this incredibly magical thing, which is, aha, I know what's going to happen next. And in order to do that, well, our laws of physics have to be accurate for the future. We can't have laws of physics which suddenly change, or if they do suddenly change, we need to know exactly how they're going to change. But if we know exactly how they're going to change, we've just introduced a new law of physics, which is how the laws of physics change. And the laws of physics are themselves still invariant. Now, this isn't saying anything about the universe behaving this way, but if we want to predict the universe, our theory for predicting the universe had better let us predict the universe, because if your theory contradicts itself already, that's a pretty bad starting place. And one lovely thing about this thing we expect, called time invariance, is, in some sense, there's a really, really lovely proof, which is that this is what gives rise to energy. I don't know if either of you want to take that over?
Yeah, I think I'll add a little bit to that. So I guess with time invariance, what we really mean by that is that we perform a physics experiment in sort of the same abstract notion of a spatial location, and then we do it an hour later, we expect to get the same result. The physical laws and the outcome of that experiment are invariant as time progresses forward. Of course, there are qualities of physics like quantum mechanics, which are inherently probabilistic, but the probabilities of these evolve in a deterministic way, which is still time invariant. So this generally holds in quite a nice way. And so with time invariance in this case, what you're really looking at is that you have a continuous symmetry in time. It can be 5 seconds later, 10 seconds later, an hour later, a day later, and the experiment will still produce the same result. And this beautiful theorem that Calvin was alluding to, Norton's theorem, states that any continuous symmetry like that, any parameter you can tune finely and get something to change like that and still observe the same thing, implies a conserved quantity directly, something that is invariant.
And one thing you get in all of science is no one can agree how to pronounce names.
Very true.
We just had Norton's theorem, I pronounced it Norton's theorem.
If we ever end up
Norton's
talking
theorem.
about the scientists which talked about matter waves,
Who
I'm
we
sure
will not
it's-
mention today. Who will not mention today.
he will not be named.
And this is the reason why we should have been recording bloopers from the start, because this whole bear thing has history, but none of you know it's really sad. Anyway, so yeah, back on topic.
Yeah, so I think it's nice to talk a bit more about Nernst's theorem and see if we can gain some kind of intuition for why it works. So I guess it's
Sorry,
nice
for
to-
context behind the whoop, I love the phrase physical intuition. It's a huge in-joke, but go on,
That's
Ollie.
true.
At this point, I'm afraid I have to interrupt your regularly scheduled programming because, well, I drew the short straw to be editing this, and in editing this, there's a rather large noise that occurs, which I don't know how we didn't realise this would come up in the thing. I guess we're just not used to doing this. But at any rate, yeah, what Ollie was going to be saying was that Rob just talked. So these are literally just reading out the words which we worked out he was saying at the time. And so hopefully he'll continue talking and everything will make sense as though this whole incident never happened. Rob just talked about how symmetry is related to conservation laws.
And a nice example of this is momentum, for example. So if you think about a particle moving in a 1D potential, well, we know that the force is kind of proportional to the gradient of this potential. So if you imagine you're trying to go up a steeper slope, then you're going to have a bigger force kind of pushing you back. Again, it's not entirely rigorous, but that's kind of the way to think about it. Exactly. And if you've got now a completely flat plane, then if you're moving kind of in this potential well, which is now completely flat, then you've got no forces acting on you. And if you've got no forces acting on you, then your momentum is going to be conserved. And so you can think of this as, well, if your potential is completely flat, then it's got translational symmetry. If you move it to the right of it, it's still going to look the same. Whereas if you had kind of a valley and you move this to the right, that's not going to look the same. From your point of view, your valley is now further to the right. And so other examples are, think about rotational motion. You've got kind of exactly the same analog. If you've got a system which is rotationally invariant, so you can change it by an angle and it looks exactly the same, then you're going to get conservation of rotational angular momentum. And then the last kind of one, which is most relevant to our discussion, is energy. You have kind of invariance in time that sees conservation of energy. And this is a bit hard to gain intuition for. But
I was really hoping that as you were going through, you were just going, oh yeah, this is easy, we can do it in the same way as all the others like, and we were just going to get an amazing
explanation.
We may still.
So the kind of one way to see how these ideas might be linked is thinking about motion and gravitational field. So let's say initially we've got a uniform gravitational field acting downwards and we're on Earth. What happens if you try and lift up a block? Well, you lift it up, it gains the potential energy, and then bring it back down, it will kind of accelerate. And you kind of can get this potential energy back when you lift it back down. You do work on it to lift it up, it does work on you as you bring it back down. However, now imagine that this gravitational field was not constant. And let's say it was on for a certain amount of time, and then it turned off. Well, if it's on, you can do, or let's say you've lifted it up, it's at the top, the gravitational field is on, you can bring it back down, it does work on you. The gravitational field now turns off. You lift it up, doing no work, because you're not doing work against anything, so it costs no energy to put it up. Gravitational field comes on.
Well,
You
it costs some kinetic energy, I feel I should point out.
Yeah, you could do it instantaneously.
Yeah, if you move it very slowly, sorry.
Exactly. The gravitational field turns back on, and you can bring it down again and kind of gain more energy. And if you do this cycle again and again, you see that you're kind of getting almost infinite energy from it for free. And that's kind of one way of thinking about how this this kind of lack of invariance in time, the fact that the gravitational field is changing, means that we're not getting conservation of energy.
And just to add to some of the intuition regarding translational and rotational symmetry, one thing would be the kind of, it's not a perfect argument, but a nice way of looking at translational symmetry in space. This kind of requires translational symmetry in time, don't at me, is that if I have a particle moving along a perfectly flat, frictionless plane, and I consider that particle a second later, it is now at a new position. I'm assuming also time invariance, but the idea is that a particle will tend to maintain its path. It will tend to maintain its trajectory, because if it was moving straight on this plane beforehand, then, well, if we're looking at a new position and the laws of physics are the same in this new position, well, it's going to still be moving straight, because by definition, nothing can have changed. The laws of physics remains the same. If you don't like the fact that I've kind of added time invariance, we can set these two particles off one after another. And from that, you can get the idea that momentum is simply the tendency of a particle to remain on the path. And one nice thing, which kind of came out of Ollie's description there as well, is the fact that this actually can give you some idea of maybe what a force is as well. So a force is simply something you're doing to break the translational symmetry of the universe. A force gives you a way of breaking this, and by that, we also can have we can begin to work out of what energy might be as well. So conversely, if I'm managing to take energy from I'm doing what Ollie magically did a minute ago to get infinite energy. I'm actually going to say I am powerful enough. I am incredibly, incredibly omnipotent. And I am going to just switch the gravitational field of the Earth on or off. Well, energy is a brilliant measure of how hard it was for me to change the laws of physics. In the same way as the force measures the amount I'm having to do to change the laws of physics with space, turning the gravitational field on and off, I must have to use some energy to do that, to turn the gravitational field on and off, because we get energy out. And therefore, you can actually use energy as a measurement of how much time asymmetry, we're not discussing symmetry of time, how much time translational asymmetry you have in the universe. Because if you're gaining extra energy from somewhere, it's not time translation invariant, and you can actually quantify the amount you change the laws of physics. In other words, you could argue that a definition of energy is the ability to change the laws of physics in a certain area from one instant to the next. In the same way, force is the ability to change it from one spatial position to the next.
And again, I then go back to the point made ages ago about how this is kind of, when you think about local systems, in that, well, with forces breaking the symmetry of the universe.
It is actually, what you don't realise is there's a really, really complex physical theory which states that actually the entirety of the universe is just carried on the back of a giant cosmic horse. It's like a post-string theory kind of theory. You won't get onto it until you learn a bit
It's
more
only got
physics.
one eye.
Yeah, that's true.
Yeah, Jeremy.
It's the universe.
Locality.
Let's go.
Forces breaking translational symmetry. Well, this force, if you kind of extend your system, so say you were kind of looking at one particle to start off with and applying a force to this means it's then kind of having a rate of change of momentum in one direction, that's simply spoken for that particle. Whereas if you kind of consider two particles together, then we know by Newton's third law that if we've got a force on particle 1 by particle 2 is being forced by particle 1 in the opposite direction. And so overall the net force is 0, and overall your momentum is conserved.
Globally. And this comes back to that idea of systems you talked about earlier, where it's how much we consider, what are we focusing in on. Because we just looked at the particle on the right. Obviously we see it speeding up, its momentum is changing. But when we look at the bigger picture, we can always see everything is as we said it would be originally.
Which I guess means it is time to introduce thermodynamic potentials.
I think there's some interesting stuff we can say about energy and different forms of energy. Really.
Yeah.
So for example, if you think about taking wood and you burn some wood, clearly you're going to be able to get energy out of that.
Yeah.
And that's just come from wood and a tiny spark, which is sort of going to be a negligible amount of initial kinetic energy you have to put in, some initial cost. But once you overcome that energy barrier, there's energy coming out. And so this isn't our normal gravitational potential energy we've talked about, our kinetic energy. It's just a lump of wood we've had sitting there. So this idea of energy is really powerful as well, if we really believe in it, in implying sort of much deeper things about physics, the way energy is stored internally within materials as well.
And so one interesting thing we might begin to ask is, I don't know, maybe something about how much energy is given out when you burn the wood. However, this is a little bit interesting because this then comes and introduces a little bit more the idea of what a system is, because I can't burn wood on its own. Okay, I probably can. Like, someone could probably make me a closed container, but if I just measure the amount of energy given out when I burn some wood, well, there's actually some subtlety to this, which is the fact that wood in and of itself is dense. It's made of carbon, and it's then going to be reacting with this external system. It's reacting with oxygen in the air, and as it reacts with this oxygen in the air, so it's going to be taking particles in from that, but it's then going to be reacting with those, and we're going to get carbon given out. And I was about to say this, carbon dioxide given out, I was about to say this produces a change in volume, and then I realised, no, it doesn't, because the number of oxygen molecules coming in and carbon dioxide molecules going out are equal. So, carbon monoxide, that's a workaround. It's not perfect combustion. And so, basically, what we can begin to start thinking about is an idea of, well, okay, we're interacting with some external system. How do we begin to, this energy we had only really worked before for closed systems, and I don't want to have to model the entirety of the universe in order to work out how much energy I'm getting when I burn some wood. At least, intuitively, I shouldn't have to do this, because I know if I put my hand over some wood, it hurts regardless of what state the universe... Wait, no, okay, probably some wood that's on fire. But it hurts regardless of the state of the universe. Splinters, that's true. Frictional energy, we've got another distributive force interacting with the system. But yeah, and so from this we actually get, I'm not 100% certain I'm going to name the correct thermodynamic potential, but the Gibbs free energy, I think. Anyway, the point is we've now started looking at a different context now. This particular context is no longer, I've got a fixed number of particles, I've got a fixed volume. That would be what's known as the internal energy. Instead, we've actually got a fixed pressure. It's the pressure of the outside world pushing in, and we don't have a fixed number of particles even anymore, but we do have conservation of the number of particles with the surroundings. And so, at this stage, energy is useless, more or less, if we're just considering the wood. What we're really interested in is a new concept. There's something conserved there. We're fairly certain there has to be something conserved there, and we can actually work this out in terms of energy. But what this ends up coming out to is what's known as the Gibbs energy, or the Gibbs potential. And this is known as a thermodynamic potential. It's weird. Let's be clear. We learned about these last year, and we had a lot of time spent being like,
why are we doing this? What are we doing this? I think you are right in that it's the Gibbs, and because we're assuming our environment is acting as a distinct sort of object, a reservoir, which is a very important notion in thermodynamics, and that this is something that is unchanging. Again, we see this common theme in physics. We want to study a problem, we want to find what doesn't change. And in this case, we assume the reservoir is so large that its temperature doesn't change. We can add in a very large amount of heat from the wood into our reservoir, and that's not going to change the room temperature nearby. Well, of course it will a little bit, but we're assuming that it's large enough that that doesn't have a significant impact.
If you can't tell by the echo, the room we're in is incredibly large. In fact, I would argue it's nearly infinite.
It's true, this room is a reservoir.
This room, I wish you could see this room. Well, I mean, you probably can see this room from wherever you are, because it's just so large.
And then also for the Gibbs potential, we're looking at pressure being the same. Atmospheric pressure is going to stay the same as well. And so these properties of the reservoir, it's more convenient to consider this slightly tailored quantity, which is still an energy-like quantity, but we've told it something about the system it's interacting with, the reservoir.
So there was quite a nice way to kind of think about these potentials, which we saw fairly recently, and I think it's quite useful to just kind of quickly go through. So start off with kind of about the most basic potential, which, again, people don't normally think of it as a potential, but it is one, is internal energy. So think about the amount of energy you'd have to put in to make the system, which may just be some gas in a container. And at a basic level, the amount of energy you're going to have to put in to make that is its internal energy, the amount of energy contained in that. And so we'll call that U for now. So let's now imagine that in making our system, we have this constraint of a constant pressure around us.
Well, which makes sense. That is doing something in air.
Exactly, yeah.
Well, we're not just making something up randomly.
Yeah, it's true. To make the system, we now have to kind of move the air out of the way. And so if this air is applying constant pressure, we're going to have to kind of provide a total work done of, this is the equivalent of force times distance, it's going to be the pressure times the volume, because the pressure is constant. And so in addition to putting in the energy, which is just the internal energy of the system, we're also going to have to put in this additional energy PV to kind of create the space. And so this is called the enthalpy, and we label this H, and this is the internal energy U plus this PV. However, we can go further. So in this example, as well as kind of having this kind of pressure, which is constant, we might also have a thermal reservoir. And in this case, as we're making our system, we might have heat, which is flowing from our reservoir into the system. And so kind of from our point of view, this is kind of reducing the amount of stuff that we have put in. So going back to kind of ignoring the air in this case, going back to the case where we have just U, just our internal energy, we kind of subtract the amount of heat which is going to be able to come in from our reservoir. And in this case, it's T times S. Probably not worth explaining that now, but just think about that as kind of the extra heat that we're getting from the reservoir. And so we call this the Helmholtz potential, F, which is U, your kind of internal energy of the system making, minus this heat that you're getting from the reservoir.
And to be clear, this is all happening. This is now our system when we're not increasing the volume as we do it.
Yes,
this is all
exactly.
It's just a fixed box in contact with this reservoir.
So this is separate to the enthalpy we calculated previously.
Yes, yeah, thank you. So F is U minus TS, U minus this heat we're getting. And lastly, we can kind of combine these two together. So we've got this kind of work that we're doing against the gas to make the space, and we've also got a thermal reservoir which is giving us this heat. And we call this Gibbs potential, G, which is, well, first of all, U, the standard energy of the thing you're making, plus this extra energy you need to put in to do the work against the gas, plus PV, minus this extra heat that you're getting for free, minus TS. And so these are kind of the different scenarios in which your different potentials are the ones that you want to consider. And we see that it's kind of very dependent on the constraints that we're applying to the system.
And so one really nice way of looking at this is, so there were lots of mathematical steps there, but one really nice thing that comes out of this all is that the internal energy, well, that internal energy, that U that we calculated to begin with, well, that's only got, the change in that internal energy is for a closed system, that is a closed box, it's 0. But then we can begin to consider, well, under what condition is the enthalpy? Sorry, a closed box, let's be very clear, a closed box that is receiving no heat from its environment, so we're giving it no energy in that way, and it isn't changing in size. Then let's consider the enthalpy, for instance, and let's consider the really interesting question of when is this constant? And we find that actually the points when enthalpy is constant, well, the points when enthalpy is constant is when you're dealing with a system that's at constant pressure, not, notably, one that's at constant volume. In other words, we can change the volume however much we like, and the enthalpy will remain constant, which is kind of quite interesting, because the internal energy then is changing. This energy, this thing that we have said repeatedly is fixed, and that this comes from time invariance of physics, an incredibly fundamental thing, that's changing. Now, the reason it's changing is because we're interacting with a system, but the point is that precisely how we define what's internal and external to our system, that's up to us, and that's up to the problem we define. And so there isn't just one energy that necessarily makes sense all the time. All of these energies are true. They're all things that you can calculate for any system at any point in time, but only certain ones are conserved under certain circumstances. Our internal energy is true as long as you never add anything to the system, and most of the time in physics we're dealing with quite fixed systems, so the surroundings aren't going to interact with it. We kind of really like to hope the universe itself is a somewhat closed system. Citation needed. However, that doesn't have to be fundamental. Certainly, as long as we are unable to simulate the entire universe, and by the way, if you are able to simulate the entire universe, please get in touch. As long
We'd
as
love to hear your opinion.
Yeah, we'd love to actually have you on. So we actually, what we're really looking for are essentially all energy is a conserved quantity that makes our calculations easier.
Very much so. And these different thermodynamic potentials we introduce that feel sort of artificial, a way, like Ollie said, of including those external constraints in our system in a way, so we don't have to play that counting game after. It's already baked into those potentials. Still just this idea of energy.
And we should note that you could argue if you lived in a universe which perhaps didn't seem closed, it seemed like it was a constant pressure, then maybe you wouldn't say the internal energy is this natural thing. Depending on how physics has gotten started, we may never have chosen internal energy as being the true energy. And in that sense, it kind of is completely arbitrary that we happen to choose it as this.
Mhm.
Yeah, so I guess kind of from here, I guess there are kind of two different routes we could now take. I mean, well, actually, from the start, I think there's several different routes we could have gone down. We've gone down this really nice route of thinking about kind of what your system is and different thermodynamic potentials.
Which tied in quite nicely with the locality idea when we thought about the two balls moving away from each
Exactly,
other.
But similarly tied to that locality, there's actually an entirely different way of doing kind of classical dynamics, which is...
Can we just be clear that I actually have no idea where he's going right now, and I'm quite excited.
Oh, I know where he's going.
Oh wait, oh sorry, yeah, he did say entirely different. Okay, up until the point where he said an entirely different way of doing classical mechanics, I had no idea where he was going. Now I've kind of gone to him. Sorry, I came in slightly too late with that joke.
Yes, essentially, that Newtonian mechanics makes certain things difficult, and so you have different kind of formulations of mechanics, which give you different insights, and in some cases kind of build in things that you would want to be in your laws, which we might discuss in a second. But anyway, these two different approaches are kind of Lagrangian mechanics and Hamiltonian mechanics. So I think that would be one nice thing to discuss.
Sorry, we have those two things to be clear in comparison to Newtonian mechanics. Those two are pretty similar.
Yes.
And Newtonian mechanics is kind of, it has some interesting properties, but it's quite separate. And one thing worth noting with these is that actually Lagrangian mechanics and Hamiltonian mechanics we have already met in the course of this podcast. We just kind of breezed over that incredibly quickly. They're actually contained within this thing we mentioned called Newton's theorem. But sorry, continue. There were other paths you were going to bring up.
Yeah, so I thought it might also be interesting to discuss kind of the idea of what is energy from a quantum mechanical point of view. So we could talk about kind of the Schrödinger equation and how this kind of incorporates energy. The link, again, we still have this link between conservation laws and, as in time invariance and energy through the idea of stationary states, where it turns out that your states which don't change in time are those ones with a definite energy in a certain system. Again, there are lots of caveats to that. And yeah, any thoughts on kind of which route we should take?
I actually had a really good thought partway through that, but I completely forgot to do it.
I thought what we go for, we want to do like a nice outline of the things we're going to discuss. So for example, it might be quite nice to introduce like what we think the general philosophies are of Newtonian mechanics versus Lagrangian and Hamiltonian. What sort of, how do their approaches differ?
I'm just still here trying to think of that really cool thing I was going to say.
Okay, you keep thinking.
I'll be here for like the next 5 minutes. These two can take over the podcast. I will not remember what it is. I'll just be sad and I'll remember it sometime later tonight. It's good.
It's been a mutiny. Anyway, so I think I'll briefly make a comment about the philosophy of Newtonian versus Lagrangian and Hamiltonian. One of the main ways in which these differ is sort of comes back to this idea of locality and globality. Globality?
Globalism?
That's
his connotations.
This is not a political podcast. Let's go with globality for now.
Just go with universality.
Yeah. Okay,
I'm back in, boys.
Locality meaning we're looking at small changes on a really small scale, whereas universality meaning we're looking at the bigger picture all at once. In Newtonian mechanics, like I sort of alluded to earlier, we're looking at these changes in dt. As we take a small step in time, how much is our velocity changing, our position changing? We're taking a very local image of everything that's going on. Whereas what's quite beautiful and subtle about the way that Lagrangian mechanics is formulated is that instead we're looking at this quantity called the action. It's this mysterious thing which we just say as a postulate called Hamilton's postulate, quite confusingly, is that when we integrate this quantity, this mysterious quantity, the Lagrangian, in time over some path, we want to look at the path which is stationary. And so instead of looking at this picture where we've got these small changes in time as they're moving along, we take this very large image. We say, which path can we take that is going to extremize this and optimize this? And that's the path that the system will take. And if you differentiate this and solve it through and look at the optimum path, you do recover Newtonian mechanics in the very simple cases that we're looking at. And so we see there's quite good agreement between the two.
And we should be clear that this sounds like Rob has just created this new thing. He's just built the action. This has come literally out of nowhere. You shouldn't believe him.
No, not at all, no.
As someone listening to a science podcast, you should be questioning every single word we say. We are complete liars. If we can make something up and get it past you, we will be happy. We'll probably not realise this at the time. We'll probably not be happy later on when we realise it.
Agonise over it in the comments.
Yeah. But anyway, my point being, he's invented something new, and you should be sitting here like, this might... He mentioned it doesn't even recover Newtonian dynamics all the time. Something could well be up here. And, you can't just invent something entirely new. And it's worth noting, and this is something which we'll probably come back to again and again and again in these podcasts, the fact that physics is not the truth. Physics is a model. And there's a brilliant quote from an MIT lecturer, Professor Alan Adams. I would highly recommend checking out his, I was going to say podcast, no, lecture series. If he had a podcast, I would watch it. He did a really good lecture course. It's on MIT OpenCourseWare. We actually all listened to it through the summer of first year because it's high quality. But one of the things he said during that is, if you see a theorist proclaiming something to be true, go up to him and punch him somewhere. And he did assume it was a man, which unfortunately probably just says more about the gender gap in physics, which isn't brilliant. So, yeah, anyway. But
Probably weren't political podcast.
We're not discussing these topics.
Anyway, but yes, point is, never ever listen to a theorist telling you something is true. Never listen to an experimentalist telling you that, but if someone claims they're an experimentalist and says that, they're probably not an experimentalist. Experimentalists should know better. I think they should all know that, no, this is all made up as heck. Yes, so anyway, it turns out this action does just as good a job as Newtonian mechanics. It's actually the foundation of pretty much all of physics that has come since that's modern physics right now, right? I'm trying to think quantum field theory, which is arguably our best description of the universe, general relativity. They both use this same thing.
It's true. I guess you could kind of describe the process of physics nowadays as you kind of consider your...
This is direct plagiarism.
I'm not certain. We may have to bleep this out.
Yeah. So you consider your constraints, you kind of write down a Lagrangian, you look at the consequences from this Lagrangian, see if it matches, and if it matches, then hey, you're done. You've done your physics and it's all good. You're happy.
he changed it up right at the end, so I think we're under the
parody. We're under parody.
Parody.
It's fine.
I'm sorry if you're listening to us. I was going to say lecturers. I can probably say first name anyway. Yes. So anyway, Rob was making this point about Lagrangian and Hamiltonian dynamics, and I kind of jumped in here to say, don't believe stuff, and physics is a model. We will never ever say. Well, we probably will say it because we'll slip up, but we will never say and mean that anything we say is true. We don't know.
Mm-hmm.
But yes, so sorry, to keep going with what you were saying, that Lagrangian mechanics as being this way of optimizing a path.
Indeed.
So I guess the question, so that's kind of philosophy behind this, and so the question is, where does... I don't know where we were planning on going with this, really.
We're still talking about energy, aren't we?
Yeah.
So how does energy come into the picture with the Lagrangian?
Yeah. So, okay. So, yeah, this is... I don't know how closely we want to... This is Noether's theorem, which we're going to talk about. I don't know how closely we want to derive it, but...
I think we can talk in sort of fast and loose terms,
So,
more or less.
to begin with, let's note this thing Ollie mentioned called the Lagrangian of a system. And what this Lagrangian of a system really means is, well, he did describe the process of physics as like coming up with a Lagrangian and solving for what happens with it. What is this Lagrangian? Well, this is the thing that I think Rob mentioned earlier about this is where you get your action from. You kind of add this up. And the interesting point about this is this quantity effectively defines your physics of a system. It all comes from this single notion of what this Lagrangian is. And all of your physics is encoded within that. It actually happens to be like a really, really neat way of doing it that doesn't require force diagrams, which is lovely.
No vectors required.
No vectors required. We are all laughing in relief right now. This is... but yes, yeah, I think you... Ollie looked like he was going to say something. I don't know if he was.
I've had a count. I've completely forgotten what I was going to say.
Okay.
It might be nice to put a name to a face in sort of a very simple system that you're working with. One
that means we're doing face reveals.
We're doing non-relativistic systems we're looking at here. Things are moving pretty slowly. Everything is sort of hunky-dory and conservative fields. In that case, the Lagrangian is just the kinetic energy minus the potential energy of your system. And so it's sort of easily calculable and it looks quite familiar in a way, but it's sort of got this sort of stranger form that caused the laws to fall out given our optimization procedure.
And most of the time with that, the aim generally is we want to try and minimize this. That's not always true, but most of the time we want to try and minimize this thing. And you can then start thinking about what that means if we want to minimize kinetic energy minus potential energy.
It's the action we want to minimize the integral of that.
Well, yes,
which is a subset
yeah.
distinction.
So we're going to, that's a good point. So we're going to consider over the entire path, we're going to consider that, which means there may be points in the path where we're doing things really badly. We may be moving for a period of time incredibly quickly and be at incredibly low potential energy. Yes, that's high action. Yes, or no. Well, as I would be called out, that's actually a high Lagrangian, not high action just yet. However, if we just very, very, very roughly and qualitatively consider what happens when you throw a ball. If you throw a ball, if you define the start and end point in position and time, which is what this requires, then the ball is going to want to spend as much time as possible, well, minimising this quantity called the Lagrangian. It's going to want to, as quickly as it can, get to a state where it has quite low kinetic energy and quite high potential energy. What would that state be? It would be very high up. It would actually be infinitely high up. But there's an issue, because it takes quite a while, if you're going at finite speeds, to get infinitely high up. And not only does it take quite a while to do that, but we are confining this at a start and end point in position and time. So it's going to have to go infinitely quickly for quite a while, well, for a finite length of time, in order to get there. And this is going to mean the kinetic energy is going to be infinite. So it can't just go infinitely high up. It must go like a bounded height up. And so this is, you can show this more precisely and more mathematically rigorously, but the idea is that you start off going relatively quickly, because that's the only way kind of you can get out of this state with very, very low potential energy. Yes, that's right. And get into a state with high potential energy. And so this is actually what gives us a parabola shape for throwing a ball. You can do the maths and it comes out far more nicely than what I just said, but the idea is you try and get up into that state quite quickly, and you try and remain in that state for quite long, quite low velocity, and then you come back down from that state because we specified the end point and said you had to do that.
Yeah, it's very nice overview.
Indeed, yeah.
So I guess the question kind of leading on from that is, why is the Lagrangian T minus D? And I guess they're kind of...
If man's going to ask this, I'm going to be impressed.
I do not have a
Ladies and gentlemen, we have a proof. This theorist is about to say something is true.
I don't be very disappointed if I just say it's because it works. And to some extent...
It's because it works.
And
the Lagrangian isn't even always T minus V.
Yeah, exactly.
Well, I'm sure, Ollie, do you want to continue on?
Yeah, so I was going to say, kind of, one way of constructing this Lagrangian is, well, you kind of work back and say, okay, well, I know that my equations of motion from Newton's laws, say you kind of already know what your Newton's laws are, and you kind of work backwards to find the Lagrangian. You know what your result should be, and you can kind of work backwards, and that's one way of finding the t minus v case. However, often you're not going to know these results. I mean, it would be a bit useless if you're kind of forming a Lagrangian. To form your Lagrangian, you always have to know your
Final Newton's laws. Yes, it
Laws,
defeats the
yes,
purpose
yeah.
of reformulating. Yeah,
exactly. And so we can say that the Lagrangian is kind of the most, often it's going to be the most general thing which obeys the constraints of our system. So it kind of obeys the fact that our system is time translation invariant. It's got these certain symmetries. Because if we know that our system is invariant under translations, then we know that our action also has to be invariant under translations. And this means often that it puts constraints on our Lagrangian. And so we can use these to kind of narrow down the possibilities of our Lagrangian.
And before we kind of move too far away, because I saw Rob rapidly jotting stuff down on his pad, before we get too far down the lines of like the practicalities getting energy out of this, it's worth noting that what Ollie said, T minus V, kinetic energy minus potential energy, is not the general form, as Rob hinted at earlier. It's not the most general form of the Lagrangian. In fact, if you're dealing with relativistic limits, there is another more complicated form which I've seen coming up in final lectures, and it's just kind of, this is the case, and it reduces to the same thing.
Exactly,
We know that it obeys certain symmetries which we want to come out, and I think we'll get on to discuss symmetries later. But to some extent, at some point in physics, you have to make a call.
And do feel free to correct me here if I'm wrong. But thinking about another very similar sort of problem-solving philosophy in physics, Fermat's principle of least time, as applied to ray optics. In that case, we're still doing the same idea of saying light will take the path which has the least time associated with it. Mm-hmm. And so in light, we're still integrating over time between two fixed points in space. In so many ways, you can view this as being very similar to the Lagrangian formulation in philosophy, except in this case, we have a very different quantity for our quote-unquote Lagrangian. We're looking at sort of, because if it's t, it's going to be the velocity of the light at different points. And so this will accumulate to the optical path length in the end.
And so one quite interesting thing, if we start mentioning this, is Fermat's principle of least time is a really lovely example of where T minus V breaks down. Because
entirely, yeah.
Because you can't do T minus V for light, certainly not classically. Mm-hmm. And so this is a brilliant example of, we've introduced this thing called the Lagrangian, we've said it's T minus V. That ain't true. It happens to reduce down if you do all the maths to the principle of least time. I think a really reasonable argument for that would be to say that a photon has somewhat constant energy. This is assuming no space-time. It doesn't even assume no space-time nonsense, because space-time, you just change coordinates. We're going to look into general relativity at some point. We're probably going to talk about this, so I'm going to save that for then. But yeah, that's an intuitive way of looking at it, but it's not something we could have said just given T minus V, kinetic energy minus potential energy. That definition wouldn't be usable, and so we're probably going to mostly discuss that definition.
In the context of mechanics, yeah.
Yeah, but in general, it's a really good point that this isn't true, and at some point there's going to be hand waviness as to why this is what it is.
Even if you're just doing it relativistically, then even when you do have a notion of T and you do have a notion of V, it breaks down that.
It still fails. Yeah.
So I guess the question is where
does that come into the picture?
And this is, I'm not really sure what the best way to approach this is. But
mathematical, just say it's mathematical jiggery pokery and move on. Sorry.
That's one way of looking at it. One way of looking at it is kind of through Newton's theorem, you start considering your conserved quantities. It's very natural to do this from the Lagrangian case. And again, the one for energy is not quite the same as how you do conservation of momentum and stuff, but it's similar. You consider this quantity and you show that it's conserved.
which is, let's just say, kind of an interesting point, right? That we can't do the time thing in the same way as we can do the space thing. We can't do the temporal symmetry in the same way as we can do the other ones, and that should have you being a little bit concerned.
Yeah.
Indeed, yeah, that's a really nice point, because if we think about Einstein's notion of space-time and relativity, a very common term we always come across, space and time are sort of treated on more equal footing. But in this case, we always see this inherent asymmetry between these two.
Which might be a nice hint that maybe there'll be a way of rephrasing it later.
I was going to say one idea, which is to see why kind of we have to treat this time differently to our position. So energy time is treated differently to momentum position. Is because in our current theory, kind of time is a parameter, whereas kind of your position is not really a parameter. So, do you
It's
have
also
some way of
weird.
phrasing that?
Imagine like a clock ticking along, and we look at our clock and we see what's going on. And we imagine this sort of absolute sense of time that is just ticking on in the universe. And it's going to be the same for everyone when they compare their clocks and so on and so forth.
There's a thing which comes up in quantum mechanics quite regularly, which is this notion of a position operator. And quite regularly our lecturers will be like, but you know there's no time operator. And that one always gets me. Because if I'm honest, I feel like I could define incredibly easily a time operator.
Yeah.
Like we define a position operator.
Wave function. It's time times wave.
Yeah, and yeah, so I could actually define one kind of quite easily. And the issue kind of comes out in arguably, like, in quantum mechanics, operators represent measurements. And what do you actually mean by measuring the time of a system? Or arguably that's potentially less well defined. You can, though. You can, or you don't ever measure the position of something in a system. You actually really say what is something that looks like but isn't the probability of finding a particle in a position. You could say what is the probability of finding a particle in a time. The issue is just that that's most of the time going to be one. You are always very, and that's kind of why we don't treat this notion in the same way.
Yeah.
But you could say, what is the probability? And I guess we implicitly do. We always do. The issue is that every single operator we look at in quantum mechanics has a very specific time associated with it. The time of measurement is like the current time. And therefore, the reason we don't really have just a time operator is because we've already assumed that in all of our other operators. And there's actually some interesting work that's been done on showing that whilst you cannot measure the position of a particle, so if you consider a rather famous experiment like Young's double slit experiment, you have light passing through two slits, it forms interference patterns, or electrons passing through two slits form interference patterns, and there's a big thing of you can't measure which path it took. That's not quite true. Scientists have managed to measure which path it took, with one caveat. They measured it over a long time period. They didn't make an instantaneous measurement at a single point in time. And they required it doing many, many experiments, and so they kind of found the average path it took. And so it's just to say that this notion I've diverged loads. Which will probably,
Energy, who's that?
which will probably be a quite common recurring theme. But it's an interesting thing to note that be incredibly careful whenever anyone says we have to treat time differently, or even that a particular theory does treat time differently, because that can actually be limiting. And like this research, when it was done, was heralded as being like incredibly groundbreaking, when not that it wasn't, but had people considered this all along, it would have been far less surprising.
Yeah, the only thing I was going to add at some point in the middle of that was kind of when you're talking about the notion that you're always going to find particles and time is one, that's going to link to the conservation of probability.
Which is in turn linked to conservation of energy.
Conservation of energy. And there's also the idea that this conservation of probability is again a local conservation of probability. You have the continuity equation, which kind of describes how probability flows from one point to another, similar to charge and current. And yeah, again, because of this local conservation of probability, we end up with global conservation of probability. Your total probability of finding a particle is always going to be 1.
Or at the very least, it's always going to be constant.
Oh, yeah, exactly.
Yeah.
I mean,
You-
we really hope there's probably one, but
That's true.
I'm just saying that doesn't actually come out of the maths.
Mhm.
It kind of comes out of the assumptions we put in some, which I guess is part of that. Anyway, okay.
And then one comment relativistically is kind of your classical dynamics, kind of ignoring relativity, is normally a map from your time parameter onto your XYZ position. Relativistically, you can't define this like global absolute time. And so you'd often use a different parameter, which is, for example, it can be anything. It can be any parameter, and now your X, Y, Z, and time are all going to be functions of this single parameter. And often, this parameter that you choose is the so-called proper time, which is the time as measured by the particular observer, the object of interest. Kind of if you're travelling along with that object, it's the time that they would measure. So yeah, there is a subtle again. Relativity does treat time differently to the way time is treated in classical mechanics.
And so, if we were probably all more confident on a relativistic footing, we could probably give you now a lovely intuition for why energy and time were the same. Does anyone know the principle of least action in relativity? Can anyone just quickly matter that off?
I think it's like minus
It's
Lagrangian minus MC squared over gamma.
does that give the
I think-
same?
No, I'm probably
But
wrong.
the issue is that's still integrated over time, or is that integrated over proper time?
Oh,
If that's
yes,
integrated
it's
over proper
integrated over
time,
proper time.
then actually, so you could follow this through, and you could. I don't have any intuition for this, but the reason time is important, or the reason we can't. All of this is us talking about why the arguments we used earlier don't work for space as well as they work for time. And that actually comes out of something Rob said early on, which is the fact that our action is defined as an integral over time.
Mhm.
Whereas, in theory, we could have it as an integral, we could parameterize our path differently.
Yes, I was going to say, clarification of what I said earlier. You can either think as the kind of relativistic action is either minus MC squared, a constant, to give you the right physics, the integration of 1 over your proper time. And the reason for choosing this is because you need to be invariant between reference frames, and so you choose the proper time because that
That's
doesn't
one
change
frame.
between
Yeah, exactly.
reference frames.
And we'll discuss stuff like proper time more later on. It's, for now, just important to know that it doesn't change.
And then, however, because we typically like to define our Lagrangian or our action as an integral with respect to normal time for a particular observer, there's a nice relation between time for one observer and proper time, and this relationship just becomes dividing by gamma essentially. And so this changes our Lagrangian to the constant we had out the front, minus MC squared times 1 over gamma. And again, don't worry about gamma, it's just a different constant depending on your reference. So I feel like we're going to do...
Gamma means fast clocks run slow. Let's get back on topic with energy!
Yes, okay, so
Okay.
we were talking about Lagrangian and Hamiltonian. Do we want to stick around there and talk
I
about
think
energy?
we haven't actually
We haven't
resolved
actually
this whole
concluded
thing.
and tied the bow on that, so...
Maybe let's talk about the link to Hamiltonians.
Well, shall we... Okay, yeah.
Because
Sorry,
I think
yes,
that's
I
the
guess we
most
could.
natural way of
Yeah.
doing it.
We're now both looking, Bob
Yes.
D and I are both looking expectantly at Ollie.
I can give it a go, and please jump in if you have any caveats. I haven't had the chance to fully consolidate these ideas yet.
Well, actually, let's maybe first, before we get on to Hamiltonian, do we want to just quickly say about where energy comes from in Lagrangian mechanics, which is that, and this I guess this kind of will come into what Ollie's about to say, but it is just something that comes out of the maths. If you were to do it in a relativistic sense, I guess it would come out. You could get it to come out in exactly the same way as our spatial and our spatial and rotational symmetries. Effectively, what happens is our Lagrangian encodes physics, and if we say that physics is observed to have some certain properties, for instance, that it's time invariant, then, translationally time invariant, then this is going to mean that our paths will have some certain properties, because the paths we're allowed are entirely determined by minimizing this Lagrangian. And therefore, they're all going to have some property, and we can think of labeling every single path we could take with some number. And what we're going to find, and this is literally just a labeling problem. And if we do go through and if we do label every single path with a particular number, what we find is that, well, there's actually, for paths that obey Lagrangians for time invariance, they have a number which is the energy. And so that's there is maths you can do to show this, but that's where it comes from.
Mm-hmm. Yeah. Obviously, we have now been going for over an hour, so I'm sure no one's listening by this point. So
I'm sure no one was ever listening to begin with, but we've got to make that assumption because, as mentioned earlier, you can't have a physical theory that contradicts itself. You can't make a podcast with voicing your thoughts with the assumption that no one's listening to it. We have to be talking to someone because otherwise, what's the point of this? We can't contradict our own existence, which I think gets a lot more philosophical than what we were planning on going on. So anyway,
It's not political anymore.
Yeah. So, well, I think the nicest way to approach the idea of Hamiltonians is starting with the Lagrangian. And our kind of and it was also quite tied to our kind of conservation laws as well. So when we're doing our Lagrangian formalism, we work in a set of coordinates, and the nice thing about it is these coordinates can be anything you like. You can choose to measure the system kind of however you want. And we will often work in terms of these coordinates, for example, x, y, and t, and their time derivatives, the velocities, x dot, y dot, z dot, where dot just means rate of change of. However, we know that when we do...
Sorry, where dot means rate of change of with respect to time.
Yes.
Just to be clear. It's not... I know rate conventionally doesn't mean that, but in case you're wondering, just to be clear.
Exactly, yeah. So we know that we've got these things called momenta, which are often conserved in certain cases. And it might be nicer to maybe see how our physics looks if we do it in terms of these momenta, sort of n times x dot, instead of our velocities, and maybe stuff will change. And there's a very standard way of doing this, and it's actually very linked to thermodynamics, but I don't think we'll go into that here.
Not in huge depth. No.
But it's worth noting that it's that in the same way we made a kind of transformation to change what we were interested in being constant. Like we made a very specific transformation with the thermodynamic potentials. We started with one thing we knew was constant or interesting in one circumstance. We made some changes to it such that it was interesting in another circumstance.
Mm-hmm.
And we're making some very similar changes. For those of you interested, this is known as the Legendre transform.
Exactly. And it turns out that this Legendre transform gives us this thing called the Hamiltonian, which in many cases is pretty much the energy.
And to clarify, we're switching out velocity for momenta.
Yes.
So instead of looking at our velocity, we've just switched this out for the momentum. And this may seem like a very trivial thing to do, like we're just multiplying by the mass.
Mm-hmm.
But as Ollie said, our coordinates are generalized. So that wouldn't necessarily mean exactly that mass times velocity idea.
And so when we say momenta, what we're kind of referring to is generalized momenta, which sounds scary, and coordinates, we're actually referring to these generalized coordinates, which would terrify me. But the nice thing is that we've already mentioned, very early on in this video actually, video podcast, shoot. I mean, you could choose to watch the black screen whilst you do this, in which case it would be a video. We've already discussed another example of a generalized momenta. We discussed angular momentum. In that instance, your coordinates are angles, or your generalized coordinates are angles. Your Lagrangian is invariant with respect to change in the generalized angle. And from that, you get a generalized momenta, or momentum, which is, well, I guess momenta, because it's around different axes, which is angular momentum.
Yeah.
And so when we're discussing these momenta, and discussing them in general, as Rob said, we are discussing these things for any coordinates, and that's why they're kind of scary. And that's why it's not a simple thing to do necessarily in all cases.
Mm-hmm. Yeah. So I guess the question is then, we've got this Hamiltonian, what do we do with it? And I guess the first thing to do is, what's our equivalent of Newton's laws? What's our equivalent of minimizing the action? We do exactly the same thing, and we can show that this Hamiltonian for our system kind of obeys two differential equations. And the nice thing about them is they're very symmetric with respect to these momenta and our positions. And this is kind of one of the benefits of our Hamiltonian coordinate system. It kind of treats momentum and position on equal footing. And that's kind of one of the reasons why it it's nice.
And you find like the more you study physics, you'll find that like treating energy and momentum as like opposite sides of the same coin comes up a lot in quantum mechanics. For instance, they're intrinsically, well, I mean, it's the same thing, that they're conjugate variables. It's the same thing that gives you this famous relation.
Position and momentum.
Position and momentum. Sorry, what was I saying?
Energy momentum.
Oh no, sorry. Oh shoot, no, that's wrong. Yeah, position and momentum. Because they're in, for instance, they're known as these things called conjugate variables, and as it happens, conjugate variables in quantum mechanics, what they are is, well, yeah, they're still conjugate variables, but they're things you can't simultaneously measure, and that's because they're linked by something. Well, in one sense, it's because they're linked by something known as the Fourier transform, which we won't get into. But it's interesting that this you will keep coming across this notions of them being two sides of the same coin. They're conjugates of one another in some complicated sense that I don't think any of us fully understand.
No.
We keep coming across
We
it.
keep giving hints of it.
We'll let you know when we do.
Yeah.
And I think it's nice to come back to now. So how does this Hamiltonian relate to this notion of energy that we've been talking about?
So, in one sense, if you got a nice, quote unquote, nice system, which is conservative, no distributive forces, then it turns out that very often your Hamiltonian is your energy. The other way of looking at it is your kind of rate of change of energy is your partial derivative of the Hamiltonian with respect to time, I believe. Something along those lines.
Yeah.
I don't remember.
Because it
Yeah.
competes with itself. Yeah, the Poisson bracket. Yeah, whatever.
Yeah, sorry, I shut some of the whole rabbit hole. And yeah, this is tricky. I'm not really sure what route to go down here.
Well, I think kind of the point is that actually, when you went through and did the algebraic jiggery pokery that I discussed earlier with regards getting the conserved quantity from the Lagrangian mechanics, what you actually find is, in general, this Hamiltonian. It's, I guess, are there any instances where Hamiltonian isn't precisely equal to the energy?
If you have funkier stuff going on,
I can imagine.
Yes, and I don't know about relativistically.
Yeah.
Also in. Oh no, sorry, I did about what I was going to say.
But yeah, so in general, this Hamiltonian thing might not be precisely equal. I mean, I guess actually, no, the really simplest example is if energy isn't conserved,
Yes.
then Hamiltonian won't be equal.
It's very clearly not equal.
Because we hope energy is, well, okay, shoot, I've gone in a circle, actually, that was cyclic reasoning. But anyway, I guess if we define energy as being the thing that is conserved under time invariance, then we have to assume it's under time invariance anyway, which I guess energy is conserved. But I guess this is diverging from what I was going to say slightly, which is the fact that part of the reason we kind of pick this Hamiltonian is the fact that actually, wait, no, I think this is kind of answers the question, which is that Hamiltonian wasn't necessarily the conserved quantity. We actually define the Hamiltonian in terms of the Lagrangian and comparing two other variables. We actually compare our positions, or generalized positions, and our generalized momentum. And then we move across and we take this Hamiltonian. It turns out these things are conserved, but that's actually part of the reason we chose our Hamiltonian to begin with. We noticed that it actually had this property that, hey, it cropped up in this one place and now it's cropping up in this other place, and because we derived one from the other, it kind of makes sense that the Hamiltonian would be conserved. I mean, mathematically they are identical statements that won't be conserved, which I think might be the nicest way of looking at it. It's just we decided to look at Hamiltonian mechanics in part because this thing was conserved. It makes sense that it would be conserved in the new thing we managed given it came from the first thing.
So, yeah. And then that also kind of, I'm not too sure what else there is to add, but again, very briefly, this is going to be a sentence. The Hamiltonian formalism passes into quantum mechanics very nicely. It And that's kind of just one benefit of it, and this is worth being aware of. But
And-
we're not going to go down that
Well,
rabbit hole today.
Well,
Later.
so there was what you didn't see there was
There's a sheet of paper being passed around.
was pointing at Ollie and pointing at me and
Mouth agape.
pointing at my paper, being incredibly annoying because I just passed a note around that said, "I think we avoid quantum mechanics for today."
That's
And
rich coming from you, Cal.
yes, well, okay, quantum mechanics and energy for today, and I think that is a good idea
Okay.
because we've been going on for ages. I think that's something we discuss. We all play frisbee. We just got a spirit circle clap there. I'm from Ollie. I'm not certain what was going on, but yeah, I'm going to suggest that
Yeah,
that
so
we
I
treat
think-
quantum mechanics another time. And
Indeed.
there is some very interesting stuff to be discussed with energy and quantum mechanics as a little bit of a hint of what may come. Energy isn't conserved.
Spicy.
Yeah,
Yes.
and was
So I think what might be quite nice is a concluding summary of what we've talked about thus far to sort of wrap it up.
well, I wasn't paying any attention to what you
No?
were doing.
Okay,
Okay.
so first off, we started off with this sort of scalar idea of energy. We had Newton's equations, we integrated them up, and we noticed there was this thing we could sort of shuffle around. If we do a force through a distance, we end up with this velocity sort of term, and we call that kinetic energy. We sort of ended up with this idea of this quantity that sort of shuffles around when we apply force.
And this is where we first got energy, like as a history of the science. I was incredibly happy when Ollie actually introduced it this way, because I was thinking Lagrangian, the formalism to begin with, and it's no, this makes it so much nicer.
Indeed.
The pedagogy be real.
And then after that, we thought a little bit more about the laws of our physical systems, how we would like them to behave. And so then we talked about this very intimate relationship that time and energy share with one another. If our physical laws are time invariant, if as time evolves, everything is repeatable and staying the same in the same way, then we expect our energy to be conserved.
And note that in everything we discuss about Lagrangian mechanics, we assume we know what everything in the system is. And so everything we've been saying here is giving rise to energy as like this fundamental term, and the reason it is giving rise to the internal energy and not say one of the other energies was solely through the fact that we have defined our entire system as known. Depending on what your surroundings are, you will get different energies. And that was what we then looking at with thermodynamic potentials, and you look at your surroundings and how the surroundings interact with your system, and that gives rise to different energies and to different things which kind of at first look like black magic and we don't understand why anyone's doing them.
We're playing this strange game of rearranging
And
letters.
somehow, sometimes it works, and our lecturer does it, and we're not certain why. Last year was fun. Anyway, then I ranted about quantum mechanics for a bit.
And then after that, we initially started off with Newton's laws, and we said, okay, we can get this idea of energy this way, but there are other formulations of mechanics that exist, Lagrangian and Hamiltonian mechanics, as we then moved on to, and we saw how energy emerges quite naturally in these pictures as well.
And it emerges from this time symmetry relation, whereas in Newtonian mechanics, we didn't really have an answer as to why energy existed, and one thing it is worth noting very quickly is the fact that Newtonian mechanics does do one thing Lagrangian doesn't, which accepts that we might not be considering the whole system.
Yeah.
You can have dissipative forces in quantum mechanics. You can say, something's happening. Sorry, quantum mechanics and Newtonian mechanics. You can have something interacting
Like a
with
drag term where you've got
drag
X
term,
term.
friction, whatever. That's all possible. That's all something you can do. It's basically impossible. There's something known as a Rayleigh dissipator, which you can use in
Lagrangian formulation.
but it's kind of a tacked on extra term. You could argue all of physics is just a tacked on extra term.
Indeed.
And with that,
And so we sort of saw, even though we started with this very sort of primitive idea of this scalar quantity that was going to be a number like 5 joules or 10 joules, by the end we were really able to put it to work, and we ended up with these differential equations. Exactly, thank you very much. And we saw that we could sort of formulate these differential equations whereby differentiating our energy with respect to this general idea of momentum, this general idea of position, we're able to sort of extract lots of information about the motion of our system. In fact, all of it in the simple cases we're talking about.
Yeah. And so with that, I think it's a case of thank you all for listening. I've been Calvin.
I've been Rob.
Why can't I say that?
Ollie.
He's been Ollie.
I'm Ollie.
And this has been a completely pilot episode of a podcast, which means, of course, we don't have a name for it. Thanks for listening.
Goodbye.